right, good afternoon, everyone, and thank you for joining us today for our colloquium series. My name is Melanie Eisenbarger. I am the Planetarium Show Specialist here at the Charles W. Brown Planetarium at Ball State University, where we are joined today not only by our guest speaker, but a classroom of students who will be watching today's talk with us. But it is my honor to introduce today's speaker, Dr. Kim Arcand. For her talk titled Our Universe Through Sight, Sound, and Touch, a Multisensory Approach for Multi-Wavelength Astrophysics Datasets. So Dr. Kimberly Arcand here is a leading expert in astronomy visualization and has been a pioneer in 3D imaging, printing, and extended reality applications with astrophysics data. She has worked for NASA's Chandra X-ray Observatory at the Smithsonian Astrophysical Observatory since 1998. She is an expert in studying the perception and comprehension of high-energy data visualization across the novice-expert spectrum. Her current projects include the sonification of spatial data, screen-based holograms, and other intersections of emerging technology and astrophysics. So we are very glad to have you here today. As I mentioned, as soon as we heard that you were going to be meeting with us, our entire office, our team here was very excited. And we are very much so looking forward to your presentation. So I will turn things over to you, and we will come back at the end for some questions.
Great. Thanks, Melanie. Thanks, Todd. It's really nice to be here with all of you today. I hope you're ready for an exciting ride throughout our universe. Just a little bit about me. As Melanie already mentioned, I've been working for NASA's Chandra Observatory at the Center for Astrophysics, Harvard and Smithsonian since 1998. It's been a while. Clearly, I'm here to stay. It's been really, really exciting working for a NASA space mission like Chandra. Just an incredible telescope, an incredible piece of technology. It's about the size of a school bus. If you're not familiar with Chandra already, it orbits about a third of the way to the moon and is still, even to this day, a technological marvel. So working for this type of telescope, I think, has sort of been just an incredible part of my life. I've been just really lucky, I think, to have access to such a wealth of data and really such creative minds to be able to work with and collaborate with. And again, having this incredible technology to bring us these views of our X-ray universe has just been very rewarding. So what does Chandra get to study? Well, a lot of things, but I'm going to concentrate mostly on things like exploding stars, areas around black holes, and colliding galaxies. These are just a few of the different types of things that we get to look at with Chandra. We're going to take a ride through all of the data, essentially. I'm a data person. I really love working with NASA data in general and Chandra data specifically. We're going to sort of dabble along with some additional friends, our other spacey friends, such as the Hubble Space Telescope, the Spitzer Space Telescope, and of course, the Webb Space Telescope. So let's take our little first tour. This is just kind of a warm-up to sort of showcase some of the things that I get to look at every day. I'm really excited to share this with all of you. You may already be familiar with many of these images, but we're going to start out small. We're going to start out with some stellar nurseries where these baby stars are forming, a very classic image from the Hubble Space Telescope that has Chandra X Observatory data added. The Chandra data really adds the viewpoint of these hot young stars that are sort of throwing these stellar temper tantrums, if you will. The Carina Nebula, or the cosmic cliffs in the Carina Nebula, as it was sort of named from the Webb folks. This is a pretty new image from the Webb Space Telescope that we just released last week with Chandra data added on top. So the original release from Webb came out in July, and this version has the Chandra data again showing those really hot young stars in like these pinks and purples and a really nice bit of diffuse emission up along that upper edge. But baby stars, young clusters of stars, other sorts of stellar clusters are really exciting things to look at with X-ray telescopes, as well as optical telescopes and infrared telescopes, because you really get such a nice picture of these views when you're using many different kinds of light. They're one of my favorite things, and I really do like them. But of course, Chandra gets to look at many other things as well, things like stars that are hanging out together, doing this sort of dance, really old stars that are sort of happily moving towards their retirement, stars that are kind of like our sun that have moved on to the next phase of their evolution. So this, to me, is always like looking at a crystal ball of what our sun might look like someday, way, way ahead in the future, like another 4 or 5 billion years or so. And planetary nebula are another personal favorite of mine and really showcase the beauty of the data from the Hubble Space Telescope and the Chandra Observatory as well. And probably my favorite kind of object in the universe, though it's hard to pick, exploded stars. Supernova remnants are just incredibly interesting things to study. You know, they're this lovely opportunity to sort of learn about the star in its life by being able to study it in its death. You know, you can't really look inside a star, not easily and not well yet. So having an exploded star, seeing its guts kind of spewed out all over the universe is a great sort of CSI crime scene opportunity to sort of reverse engineer what that star was like in its life. And this kind of stellar guts are just really, really lovely, especially when you've got X-ray data from Chandra. Chandra also gets to look at galaxies of all shapes and sizes. So the Whirlpool Galaxy is a lovely example of the sort of beautiful spiral structure with a smaller companion galaxy on the left. The Cartwheel Galaxy, this is another image from the Webb Space Telescope that was released earlier this year that we've recently re-released. I think it was just last week, with the Chandra data added in, where you're sort of seeing this X-ray bridge between the large spiral galaxy on the right and one of the smaller companion galaxies on the left. And of course, other types of galaxies that look like exclamation marks, things like supermassive black holes, where it's just like the heart of the galaxy beating and pulsing out this material. Clusters of galaxies. This is another image made famous recently by the Webb Space Telescope. In this version that we also re-released last week, we are now looking at that same field of view from Webb that's also been included with a little bit of Spitzer Space Telescope data. So a little bit more infrared data that you're seeing in some of the yellows and greens. And then also the sort of cyan blue from the Chandra Observatory that shows that really nice shock wave that looks kind of like a bridge structure between that little group of galaxies. And of course, some really fascinating objects like clusters of galaxies that are really fascinating because they can kind of help us learn about the very existence of the universe itself. And some of them that look like they're smiling back at us thanks to gravitational lensing. And I always like to try to insert smiley faces in my talk wherever I can. So how do we get this fantastic data? Well, it's really fascinating feat of engineering, right? There are these objects pretty far away from us, and that light is traveling to us over those thousands, if not millions or billions of light years. And all of that, all those photons, those packets of energy are being captured by, in this case, Chandra, for example, in the schematic, and it's being packaged up into a digital suitcase in the form of ones and zeros down at the base of the telescope. And then that digital suitcase is being shipped down to Earth through NASA's Deep Space Telescope before it sort of has a hop, skip, and a jump to the Jet Propulsion Laboratory, and then another little skim over to the Chandra Control Center, which is up here in New England, up in Burlington, Massachusetts. So once we have all of this data, all this sciencey goodness that the telescope collected while it was doing its observational schedule, then what do we do with it? Well, we start to unpack that digital suitcase. And unpacking that suitcase can take, you know, a little bit of work to be able to run the software, run the coding, to be able to first create your table of information, the time, the pixel values, and the X and the Y's, the energies of each little photon, each little packet of energy that struck the detector during the observation. And then we've got our raw data, and there are likely steps along the way, whether you're plotting that data, whether you're looking at the spectral information, that sort of DNA or fingerprint of the light. But I wanted to jump to the image-based part of the process. So at this point, we're going to stay with one very dear friend of mine, the Cassiopeia A supernova remnant. It's a really classic supernova remnant. It's pretty close by. It's just about 11,000 light years away from us. So we have a really lovely view of it in our Milky Way. It's a great object for high energy telescopes like Chandra to look at. It's a very famous object that most telescopes probably around the world have looked at, and many of them repeatedly, because we have such a perfect bird's eye view of this supernova remnant as it evolves and changes. So this first image that I'm showing you is some of the raw data that we got down from the telescope back in 1999 after Chandra was first launched. This object was considered Chandra's first light. It was like the first official image released from Chandra. And you can see right away, the scientists, the engineers that had worked on this telescope were very excited to get this image because Right in the center of that data set, you've got a nice bright white spot, and that is the core, those leftover bits and pieces of the star that exploded, the neutron star. And it was really lovely to have a sort of visual confirmation of this after looking at this object with Chandra for only about an hour. So this was a very, very exciting moment way back in 1999. But this is a classic object. So we've looked at this object again and again. It's also one of our calibration targets. So that means that this object really helps us understand the sort of health and safety of some of the Chandra instruments. But being able to use it as a calibration target also means we get to pack in lots and lots of data of it. So now we have about, I think, almost 2 million seconds of observation time of this object. And so the image now on my screen, it's the same view of Cassiopeia A. It's about 95% X-ray data still. There's a little sprinkling of optical data from the Hubble Space Telescope, mostly in the form of a star field and a little bit of that sort of wispy gold stellar structure all through the middle. And then the rest of it is the X-ray data that we've been able to cut up by essentially the chemical elements of this exploded star. So using that spectral analysis to be able to understand where the iron is, you're seeing that in like the purples, for example, where the silicon, the sulfur, the calcium is, and that's in the greens and the sort of oranges, and a little bit of those pinks. And it's like a really incredible weather map that we've been able to create to be able to understand where all of those chemical bits and pieces are located in this stellar remains. So having access to all of that data is really exciting, but when you have such a strong data set, you can do a lot more with it. And in this case, this was one of the very first objects we were able to ever translate into 3 dimensions. We worked with Dr. Tracy Delaney, who was at MIT at the time. She was using some spectral data as well as some infrared data from the Spitzer Space Telescope and some ground-based optical data from a couple of observatories as well to be able to figure out, which of that light was blue shifted, which of that light was red shifted. And we worked on this 3-dimensional object using some very interesting software borrowed from some colleagues at some local Boston area hospitals to be able to create this first representation of it in 3 dimensions. And it's really useful to be able to look at objects like this in 3D. You definitely, besides understanding what other material is moving away from you in that red shift and what's moving towards you in that blue shift, but you're also being able to understand like what this star did when it exploded. And in Cassiopeia A's case, it really turned itself inside out, which was pretty interesting to be able to see when it was in a 3D representation. But also the different sort of phase of it, the different phase of that sort of spherical structure of the explosion from that main bit, and then also those really slicing jets that came out after. And again, 3-dimensional modeling makes that sort of possible to view in a really, I think, interesting way. But one of the cool things about having a 3D model is that you can then do a whole lot with it. Besides just study it, you can also 3D print it. We've been running a program for the past maybe 8 years or so with 3D printing objects like this and working with the National Federation of the Blind and then other students who are blind or low vision to be able to really improve how we understand and create and print objects like Cassiopeia A in 3D. And if anyone's interested, by the way, and has access to a 3D printer, you can go to the Chandra website, go to chandra.si.edu/3D print, and you can access all of these files to 3D print yourself. So it's kind of cool because you can hold a dead star in your hands, albeit like scaled way down, because this is like 40 million billion times the surface area of our sun. So it's, really tiny version of what Cassiopeia A would be like in real life and, in hard plastic. We can also bring it into virtual reality. This is one of my students, and she's going to be walking around inside that exploded star, which is, I think, another cool way of understanding and learning. You can bring it into augmented reality. This is a project where we worked with the Microsoft HoloLens to be able to turn all of the layers on and off. So you can sort of build this supernova from scratch. You can, add the jets, add the silicon, the sulfur, the calcium, the iron, and turn each layer on and off at will. I'll just let it play for a second so you can see this person interacting with it. You can see them turning on some of those layers and turning them off. And then one of my favorite projects lately has been taking that data and bringing it into sound, and being able to take image-based data or spectral-based data and translating into another medium such as sound has been very rewarding, way more rewarding than I ever expected. This was a project that we started during the pandemic because at the time, well, everything was just kind of crazy and we couldn't get to our labs. Our students had to go home. We couldn't get to a 3D printer or to a VR space, and it was just a strange time. And so I started working with some colleagues at Systems Sounds, Dr. Matt Russo and Andrew Santaguida, who are not only into astronomy, but also into music. And together we started this project of sonification. And this is what it sounds like when we translate Cassiopeia A, our very dear friend, the exploded star, into sound. So all of those different versions of Cassiopeia A, all of those different iterations, whether a two-dimensional image of various kinds, whether a 3D model, 3D print, virtual reality, or even sound, they all came from the same package of binary code. And this is a bit of a slice of that data, just a tiny little snippet of those actual ones and zeros from the Cassiopeia A data set that are up on my screen now. So I think it's a really interesting case study to be able to take a rich data set like Cassiopeia A and just slice it and dice it in numerous ways to be able to figure out what it is you need and to how to best serve the folks that you want to be able to bring this data to and to be able to provide access to. So it's been a really fascinating experience, being able to work with the data in these different ways. And part of the reasoning for taking this approach is to make data accessible. For the first, 8, 9, 10 years of my career, I was really working on just the visuals, like how do we, squeeze out all of that lemon juice from those data and make some really lovely lemonade with it. And that took a while. Working with X-ray data is not always easy. It takes a different kind of mindset sometimes, and you have to really work with it to be able to understand what's going on and what needs to be showcased and what the science story is, to be able to really optimize that data in a way that makes the most sense, is also authentic to the data, and really drives home the point of the scientific story. But when all is said and done, X-ray data, well, none of us can see that inherently. None of us can see that natively. There's no human born that can see in X-rays. And so why not prioritize other ways of knowing, other ways of experiencing, other ways of making meaning for a type of data that none of us can naturally see. So X-rays, I think, have provided me at least a really unique opportunity to think outside the box, because it's not the classic look of an astronomical image that we think of when we think, Hubble Space Telescope data. Capture through your telescope at night, looking up to the night sky. I think X-rays in particular have really given me an avenue to try different things, because it is a very different kind of looking photon that's been captured, if you will. So we've been taking this approach to Chandra data for a while now. We've been building up a library of three-dimensional models as we can. Creating three-dimensional models of these cosmic objects is hard. It's not easy. We don't always have as many photons as we'd like, just from Chandra, for example, and even buddying up with other of our space telescope friends like Hubble and Spitzer and now Webb and others doesn't always give you the optimal results either. But with a lot of really sort of good persistence, and also working with our friends who do modeling, doing some computational models, those mathematical models that really help fill in the missing pieces, we've definitely been able to come to some success. On the screen now is the Crab Nebula, an object you might be familiar with, a really lovely pulsar. And we've had some good luck with objects like this. Exploded stars, I think, tend to be a specialty of Chandra. So we've had a lot of really good luck with the data. The high resolution really helps, of course, and other data supporting from various telescopes as well. So right here is just a little small collection of some of the objects that we've been working on that are all 3D printable if you wanted to check those out. It's mostly stars in different stages of stellar evolution. And I really have to give major kudos to our colleagues who are blind or low vision for helping make these 3D prints and 3D models way better than they ever would have been otherwise. Their perspective on approaching the data in 3D form has been just absolutely invaluable. And to showcase that Cassiopeia A is not a unicorn in this sense, I wanted to showcase one other object. This is yet another exploded star. I will talk about a few other things later, I promise, but just one more, if you'll let me. This is Tycho's supernova remnant, which was first witnessed on the ground back in like 1572, I think. It's about 13,000 light years away from us. And it's this really lovely structure in X-rays that I think I have a version later that shows just the optical view is just completely missing when you're looking at it in certain kinds of optical light. So having the opportunity to work with data sets like this is great. And again, there's also three-dimensional modeling of this, some hydrodynamic simulations, for example, and other modeling that are bound by the observational data. So you can get a really nice 3D model and a 3D print, for example. And then we've also taken this and sonified it as well. And I will say every time we sonify something, I learn just something a little bit different, a little bit new about that object, because it's almost like I'm overly familiar with this data. I've worked on it so long. It's so familiar to me that sometimes things can slip by. And when I explore an object in a different method and a different way of knowing, without doubt, I will find something new. I will discover something new that I never noticed before. And that's been a really exciting opportunity for me. So the point of working with data sonification for me has been working with colleagues who are blind or low vision, working with non-experts who are blind or low vision. Without doubt, the benefits come back to me and people who are sighted as well as just another way of being able to really extrapolate some new information and some new meaning from these data. So I'm just going to play the sonification in pieces. So right now we're listening to the optical layer being sonified first, and it's just a lovely harp as we extrapolate out. So a dear colleague of mine, Dr. Wanda Diaz, who is an astronomer and computer scientist who's been blind since she was a teenager, she actually did her PhD thesis on how you can become a better listener as a scientist, as an astrophysicist specifically, that the power of the human ear, I think, should not necessarily be considered, just later. Like it really is another way of knowing. And her PhD thesis on showing how we can become better listeners to scientific data was really, well, I want to say eye-opening, but I guess I should say ear-opening, because I started thinking about data in a new way because of her research. And so these types of applications just do have additional value. Here's the second piece of the Tycho supernova remnant sonification, and now we're going to listen to just the X-ray. And you're hearing that in like a swirly sound. I don't know if it was obvious to you, but there was a bit of a crescendo with that shock wave around the very perimeter. And then here is the spectral map. So for the spectral data, those frequencies of light have been interpreted as frequencies of sound and shifted about 50 octaves. And now this is the combined version of the optical, the X-ray, and the X-ray spectra all together. And so all of those sounds, they really impart different kinds of information. In that spectral data, there were 3 little peaks that might have been audible. There was one peak due to the iron, another due to the silicon, and a third to the sulfur, for example. And then even when you're listening to that full composite, you can clearly hear the delineation once you get past that shock wave and then you're out into space and you're just hearing the sound of the stars. So it's a different way of representing data, but it is, I think, a really interesting area for growth and future research. I want to play just a few snippets. I feel like I'm doing okay on time. So I want to play a few more snippets of these sonifications, if you will indulge me. I am just obsessed with them lately, and happy to talk a little bit more about the hows and the whys after. These are all bespoke data sonification. So it's not like just running data through a single piece of software and like a factory kind of popping out results. They're bespoke in the sense that each data set has a different science story, and each data set has a very unique set of data, the way they look, the way they are. And so each one we've been finding really has its own story that needs to be told in its own way. And so I think what's interesting as you're listening through these examples, you'll hear very different examples of sound. So this next piece was one of the first ones that we ever did. It's probably still to this day one of my favorites because I actually worked on this image, putting it together, I want to say back in 2008, 2009. And then when I heard it back in 2020, it just made the data new and exciting for me all over again. So right now we're going to listen to the galactic center. So see, no more exploded stars like I promised. We're going to move away. All right, there might be a few exploded stars in here, but they're tiny little blips, so I will not talk about them. Mostly we're going to be listening to all of this sort of downtown area around the galactic center of our Milky Way galaxy. We're going to be exploring this inner 400 light year span as we get closer and closer to the area on the right where Sagittarius A star, the supermassive black hole, actually resides. You'll hear crescendo as all of that high energy data really sort of starts popping. So there are 3 different layers of information in this sonification and in this image. We've got the lowest energy material from the Spitzer Space Telescope. We've got the sort of mid-range energy from the Hubble Space Telescope. That's in the yellows, the Spitzer's in the red. And then the blues and the purples are the highest energy material from Chandra. And so the sounds are sort of similarly interspersed. The lowest energy material from Spitzer is the piano. The sort of medium energy material from Hubble is this like plucky violin sound. And then the highest energy from the X-ray telescope is like a glockenspiel type of sound. And so just, be on the lookout or the listen out for that supermassive black hole. Here we go. what I like about that sonification is that this is a very rich data set. As you can tell from the visual, it is very dense. There is a lot going on. That beautiful filamentary structure from Hubble, that sort of, cloudy, gassy, red material that you're seeing from Spitzer, and then all of those tiny sources from Hubble, as well as some of the diffuse X-ray emission that you're seeing as that sort of nebulous, bluish, purplish kind of material. It's a lot to look at, and it's a lot to listen to. But when you listen to it, the interplay of the three different instruments is, I think, pretty evident in certain locations. You can really hear how the material through sound is complementing each other. So now let's listen to another piece, another not exploded star. This is the stellar nursery, the pillars of creation, that very famous image from the Hubble Space Telescope that we've added the X-ray data to as well. And you're going to hear a couple distinct things here. And in this one, we really wanted to make sure the structure, that sort of three-dimensional structure of those pillars, those really tall columns of gas and dust, was very evident. And then you'll hear the clear delineation of all those hot young stars from the Chandra Observatory as well. So here we go. And so perhaps unsurprisingly, this sonification was voted the most spooky sounding sonification on NASA's SoundCloud for their sort of scary Halloween sounds playlist, which is perhaps not a surprise when you listen to that. And what I like about it, again, is you can clearly hear the richness of the structure of those pillars, but then you're also getting that sort of mapping of all of those hot young stars around it. The next one is a piece that we released back in May that we thought did very well back in May when we first released it. This is the Perseus Galaxy Cluster. I love clusters of galaxies. They're such fascinating objects, and what they have to tell us about our universe is just fantastic. This image was very special to me because the data, going all the way back to 2003, we've talked about this object as, having the deepest note in the universe. This supermassive black hole at the center is just belching out this material and into the hot gas, and it's just causing these wonderful pressure waves, these sound waves that we can actually translate to a note, B flat, about 57 octaves below middle C. And so we've had that story in our heads for ages. We first worked on it back in 2003, and I loved that story back then. I've always thought this data set a very special one. So when we started the Sonification project, this one was very high on my list, wanting to translate, because I wanted to see, or hear, I guess, if we could take that data set and translate it into sound, being very true to the fact that this already had sound waves in it. So taking that note and sort of scaling it back up into the realm of human hearing. And so that's what we did. We sort of re-sonified, I guess, if you will, a sonification of a sound wave was new to us, and that was very exciting. So we released this back in May, and we were very happy that people seemed to like it, and it did well out there in the universe, so to speak, of media. And then some colleagues at NASA just tweeted about it again on a random Sunday in August, and it was a very slow news day, and this went hugely viral, and about 1,200 news stories came out over the next week or so, with the overall news aggregate metrics around 2 billion people would have been exposed to this story potentially. And that's a ridiculously large number of people that could possibly have heard of or come to read about this cluster of galaxies where a supermassive black hole is belching out into the universe. And the idea that these supermassive black holes could perhaps act like divas out there in the universe with their own note to sing, I think was a really interesting concept for people to think about. So The overall sort of lesson from this for me was that one, obviously this went well beyond people who are just blind or low vision to people who are sighted being interested in this as well. And I think that anytime you have something that is universally designed, hopefully the idea is that it will be useful to more than just the target audience. So you can think of things like closed captioning that are now kind of ubiquitous, and cut curbs that are ubiquitous. So people who have a wheelchair can use them, but people who push a stroller can use them, and a cyclist hopping over a curb can use them, and someone on a crutch can use them, and all different cases, right? And so this piece I think was really exciting just to see the breadth of the interest in it. So if you haven't heard it before, here is the Perseus supermassive black hole sound. That one is unsurprisingly also going on the NASA Spooky Sounds of Halloween playlist. So a lot of the response to that was either it sounds like something Hans Zimmer might put in a movie, or also it sounds like something, you know, Michael Myers might appreciate in a horror movie soundtrack. So hopefully it didn't scare too many people, but it was really fun to see the response. And the last sonification I'll play, I promise, is yet another not supernova remnant. This is Chandra Deep Field South. It is an incredibly rich data set, the deepest X-ray data set captured, to the scientists beautiful, perhaps. For those who aren't visual in the audience, it's kind of like a black rectangle with a bunch of multicolored dots strewn across it. And that image perhaps might not sell the story, but the story is really fascinating. Being such a deep observation, this is essentially a population of black holes that hadn't been known about previously. And so now we've got like thousands of black holes that we can listen to essentially in a data set like this. So I was really hoping that a sonification would help tell the story of like a dense population of black holes, I guess, better than just an image that might not be as obvious to people, especially to non-experts. So in this case, the point sources, those little packets of energy, those have been cut by the energy levels, with the lowest being the low sounding notes and the highest energy cuts being the highest sounding notes. So you'll hear that sort of distribution as we scan the image from bottom to top. So here's what like thousands of black holes sound like in a sonification. So yeah, the universe is a really beautiful place to listen to. And I do have one more sonification that I'll just play a tiny snippet about. I snuck this one in at the very end. This is a new one from data from the Webb Space Telescope. Just play just a tiny little snippet. Stop there. Just an example that it takes all different kinds of data that you can use to be able to make these really interesting sonifications. And I should say overall, we've had an incredible response to these sonifications. I am desperately trying to finish a paper on sonification research that we conducted last year. We had a study of about 4,500 volunteers, and what we learned from them, both sighted and people who are blind or low vision. And what we learned in that study is that these sonifications definitely do increase learning. They really increase enjoyment and overall engagement with the data. But also beyond that, they also really provide emotional responses. A lot of the open-ended questions were just covered with emotional responses. They make me feel happy, scared, sad, joyous, exhilarated, fascinated, all of these different very sort of strong words that people were able to provide us and as to how they perceived and reacted to translating data into sound. So it's been, I think, a really interesting journey, taking data sort of out of just the visual, not always prioritizing just the visual and bringing into different areas, working on this data by using, different methods through touch, through sound and through sight has just been an absolute joy of my career. We've been working on different kinds of hologram-based representations. We've been using the sort of haptic information. So for example, phones that have vibrational information, you can provide a haptic response to data as well. So there's all of these different methodologies that can be applied to data representation, data vivification, to be able to really extrapolate out all of that sciencey goodness and represent it in a unique way. So I will stop there. These are the things I like to think about and talk about. I love to do things like write books about it as well. And if you have any questions, I'd be happy to hear them, but also do feel free to check out the Chandra website, because everything we do is free for other people to access and to use. So if you want to hear more on the sounds and learn a little bit more about the details of each sonification, that's all provided at the first URL. If you want to learn more about what we're doing with our colleagues who are blind or low vision, you can go to the tactile site. If you're interested in VR, you can also see that one. And I believe I provided a couple other URLs throughout this talk as well. So I will stop there, and I guess we can go to questions.
Excellent. Thank you so much.
Well, thank our speaker.
Yeah. As we switch over to questions from the classroom, I do actually have a question of my own. So do you think, in your opinion, that it's better to focus on maybe one sense at a time? So for example, touch, sound, or do you find that things really don't get overstimulating, like the more the better?
Yeah, I think there's not an easy answer for that, because it really depends on the person and also the situation and also how it's being combined. So right before the pandemic started, I had originally began some work on taking the virtual reality piece that I showed earlier of that exploded star, Caspia A, our very dear friend, and in the virtual reality space, using the sort of geospatially or astrospatially aware data to attach sound to it. So being able to maneuver through virtual reality as someone who's blind or low vision, it's not always going to be the most appealing experience. But if you can attach a layer of sound to that virtual reality, that provides a little bit more of a layer of data. And then as we were starting to think about that, we started experimenting with how you could take your phone, for example, and the same thing, get some haptically smart response as you're walking through different parts of that exploded star. So a different kind of, buzz for if you're in the iron section versus in their silicon and the sulfur. And that was going along swimmingly, but we did pause it for the pandemic. And really, once this stuff started picking up, we haven't been able to get back to it. But I will say in that sort of preliminary work that having the option for flexibility was key. So for somebody who's sighted, just listening to sound can be taxing because they don't necessarily have the experience of listening to sound in general and being able to navigate that to create their mental map. So for people who are sighted, having both the visual and the sound is very helpful. For people who are not visually oriented, of course, not having the visual is not a big deal. Having the sound and then having an additional tactile response can be helpful. So it seems like having at least two senses at one time tends to be helpful for more people. But that is, I should say, a non-scientific assessment. That is just a sort of anecdotal assessment based on the work we've done so far.
Excellent, thank you. We will definitely need to add some of those sonifications to our Halloween show that we have going on this month. Maybe playing them beforehand would be really fun. All right, we
Yes,
will.
absolutely.
It sounds really exciting. We do a spooky soundtrack beforehand, but I think combining it with the science we're teaching would be great. We're all about it.
I love that. That's great.
We will turn things over to questions from the classroom.
Caleb?
Yes, I have a question. The one the same last one you showed about black holes. I noticed that there are different pitches for each sound each black hole made. Is that indicative of properties such as mass, or activity, or other properties?
Were you able to hear that?
No, it sort of got a little bit choppy for me.
So the question is, the one that you were showing the different was the 1,000 black holes.
Yeah.
What property is responsible for the different pitches? Is just the intensity of the X-rays, or?
It was the energy cuts of the X-rays. So the lowest energy sources were in the sort of lower notes. The medium energy X-rays were in the medium range, and then the highest energy X-rays were in that sort of highest range. And that field is sort of a collection. It's primarily black holes, but also galaxies with very bright supermassive black holes, right? So you're going to have differences in the energies, the energy cuts, if you will, based on exactly what type of object it is and the age of it, and also like things like distance and all that. So those sounds are just sort of helping give you a map of the distribution of those different types of energy cuts throughout that sort of data.
And so the brightness would probably be the volume?
Yes, exactly. So brightness is a volume. Yep. And also from top to the bottom, I believe we had a slight difference in like the location from left and the right, but I forget what that sound was. I'd have to go look it up. However, if you go to chandra.si.edu/sound, you will see the exact specifications that we selected for each of those with full explanations of like why.
Cool. Any other questions? No?
And sonifying these data sets reveal things that can't be directly inferred from spectral data.
So can the sonification give you information that can't be inferred from the spectral data by itself?
Yeah, so that's another great question, because I think there are a lot of people doing active research into the viability of sonification to really improve research methodologies. And not just in astrophysics, but in all sorts of different fields, in medicine, in molecular biology, in just various fields across the board. And I think what's exciting there is that the potential for the human ear to be able to pick out data better, more efficiently, is really huge. So they call it sort of like the cocktail party effect. If you're at a cocktail party, like, I don't know, pre-pandemic, I haven't gone to a cocktail party in a long time, but whatever, back in normal times, if you're at a cocktail party, you might be sitting on a couch and you're having a brief conversation with the partner next to you, and across the room, you hear some of your friends making a couple comments on last night's game. And in the kitchen, you hear the host is washing a few glasses and setting up a few plates. And then in the dining room next door, you're hearing a dog walk around hoping for scraps under the table, right? You're sitting in your spot, but you're hearing all of that information throughout those couple of rooms that you're near, and you're able to pick and parse what you need, right? So the human ear is really adaptable and really good at sort of sorting through that signal to noise. And so there are definitely areas of research where that ability has true viability for improving research. Things like variable stars, for example, have definitely been studied as far as the ability for humans to more efficiently sort through all of that data versus just looking at plots, right? And the ability for humans to pick out data in a really like noisy data set, for example, I'm trying to think of like, even in my own experiences when I was listening to, I think it was the Galactic Center for the first time, like I had heard a section where the infrared data really filled in a complete like sort of, cavity, where there was just very little X-ray data and optical data. And I just never looked at it before. I'd never seen that before, because that field is just really densely populated. There's so much going on. And it just made me think, all right, what is happening there? There's, I think, a lot of opportunities for sonification to be able to supplement that type of research. And that's, I think, going to be remarked upon more and more as people do this type of work and also study that viability of having that kind of impact. So yeah, I hope that helps. I think, again, it's a huge area of research. And I'm very excited to see what other folks can do to sort of showcase the usefulness of this as a data tool, especially as we get more and more big data, right? Like the problem right now, we have a lot of data, and that's fantastic. I will never complain about having too much data. But when you have that much data, you have a responsibility to sort through that data and parse it all, right? Like data that's sitting in archive has some potential value. It's the data that you're working with, that you're analyzing, that has like the true value. So that process of going through all that data has to be figured out. And especially as bigger telescopes and other kinds of, scientific instruments come online, the human methodologies for sorting through that data will have to improve. And I do think sonification is one area that can help us with that.
Yeah, I think there's a full dome presentation of, I forget the title of it, Einstein's gravitational playlist or something like that, where they do some quantification of gravitational waves.
Oh, I love that. Yes, definitely.
So that's out there.
It's funny you mentioned variable stars as well, because that's a big area of research at our university. So something we'll have to look into.
It? Great. Okay, well, I hope someone's sonifying the data then, and they can let me know how's it going. I would really love to hear it.
Cool. Any other questions from our crowd?
Maybe all the music was like a lullaby and put everybody to sleep, in which case I apologize.
We should have ended with a really scary one to wake them back up. I do have one more question of my own here. I know you are a huge role model to so many of us here. Do you have any role models of your own? I know you didn't always work in this specific field, so I was wondering kind of when things changed for you.
Yeah, oh my gosh, first of all, thank you. That is so very sweet of you and very kind of you to say. And yes, I am a transplant, because I originally started out in biology looking at things through a microscope, and then eventually the macro won over the micro, and I was pulled into astronomy, and I've never looked back. Though maybe someday I'll return, who knows? But absolutely, gosh, too many to really count, because yeah, like science is hard, and I'm in computer science too. So computer science is hard, and the representation has not always been great, is not always great. There's definitely like feelings of isolation that can happen when you're sort of feeling alone in those fields. And I'm definitely sort of sympathetic to people that feel like that. Growing up, my parents, mostly my mom, were just like really supportive of me, no matter what ridiculous thing popped out of my mouth. Always been like a dreamer, think big type. They supported me even when I said like I wanted to be an astronaut, but could like barely handle going on the tilt-a-whirl. They never doubted me. So I think having people like that has been really important. Honestly, the two women that helped launch Chandra up into space have been role models for me as well. They're just very dear people. Colonel Eileen Collins was the first woman to command a NASA space shuttle mission. And I've just looked up to her ever since. And also Dr. Katie Coleman, she was a chemist and an astronaut. And she's now retired, but she's just been an absolute force to see, and how supportive she is of other people, particularly underrepresented groups in science and technology, and everything has been really exciting. So I look up to people like that as well. And, the fact that she sent Chandra on its way to work from the space shuttle is also pretty amazing. So I have to say, different people along the way have been really supportive. my computer science professor that like tucked me under his wing, even though I was not a computer science major at the time, was another person that had a huge impact on my life. And I don't think how much they realized the impact they were having. So all of that is to say, like, it takes the village, to raise a STEM person, essentially. And I've been very lucky to feel so included and to feel so supported, because when you feel included and supported, you can go out and do fun things and try different things and not worry about it, not feel like you're going to be ridiculed for making sound, which I can be honest, a few people thought was very, very odd when I first started doing it with my colleagues. But it was okay because I knew I had support of other people. And yeah, I can't really thank people like that enough. And I really try to help fill that role for other people whenever I can. And who knows if I'm doing a good job at it, but I guess maybe in 20 years or so, some of them will give a talk someday and make a nod. Who knows? that would be nice if they did. So
Absolutely. Any other questions from the classroom?
Tony.
Just wondering if you had, for your 3D print things, are you basically interested in sort of visual information, or is there anything to be gained by touching or exploring with your touch or anything like that?
So we're able to hear that?
yes. Yeah, that one I was able to hear. So, yep. Like with the model of Cassiopeia A, for example, we specifically worked with students who are blind or low vision to be able to make sure that those models added value, to make sure that those representations were understandable and knowable, were both something useful, but also a pleasure to be able to experience for them, because I really felt it was incumbent upon us to be able to, I have this really awesome job. The image behind me, like, this is what I get to do all day. Like, I get to play in a sandbox of data, incredibly rich, awesome sandbox of data. And I'm taxpayer funded. So like, I can't stress enough how important I feel it is to make sure everybody comes into that sandbox with me. Like, I don't want to be sitting alone in the sandbox building a sandcastle, right? I want to like have all my friends in the sandbox. I want to make sure like a lot of people have access to that sandbox, as many as possible. That means I will have done a job well done, right? And so when we were working on that Cassiopeia A 3D print, I'm like, okay, well, we did print it. That's great. That was a technical feat. First time we'd ever 3D printed an exploded star. Cool. But does it add anything? And that's when we started working with the National Federation of the Blind. And so the students that we worked with, about half the class was blind completely and half the class was low vision. And so it really was a study to make sure that what they were feeling, everything that they were touching, made sense. And also they really changed how I understood that model. They wanted to explore it from the inside with their hands. They wanted to be able to feel all of those ridges and the jets, for example, that are, these beautiful jets coming out of it, but they're so tiny in comparison with that large spherical blob. So they were fragile. And we really had to fix that, because just a little bit of overhandling of those jets that they wanted to be able to explore meant that they would easily snap off, right? So we started doing things like cutting the models in half so they could explore tactilely the internal information as much as the external information, and then attaching them with magnets so you could put it back together. And the same thing with the jets. The jets were then attached with magnets so that even if they fell off, you could easily put them back on. They could be explored individually without breaking, and then reattached to the model. And so according to the students that we worked with, subsequent sort of analyses of that experience, they really did say that they represented an improvement in how they could experience astrophysical data, because it's a very different thing to explore a model in 3D with your hands than it is to just hear about something, or to just be told something, to just have a screen reader, reading the text about it. And so it was, I think, exciting for me to understand that tactile exploration also had value. How much value that has for an untrained researcher that doesn't need to explore the word tactily, I don't know. And I don't think that we can say at this point. The research on that would also be warranted and wonderful. But for people who are blind or low vision, having these alternative methods of being able to explore the data are great. And I will say we've had an amazing amount of success with the 3D prints with children, even adult learners of, different learning needs, for example, things that we just didn't expect. Again, we made them for a specific population, but I started just taking them out with us kind of whenever we went to an event, to a conference, a science conference, education conference, whatever it might be. And over, it was really gratifying to see people just wanting to touch parts of their universe, right? Just wanting to touch these things and explore them in a way that they hadn't been able to previously. So, we don't have an exact qualification of what kind of value that's imparted exactly, but anecdotally, the response has been, again, just very, very gratifying. So I hope that helps answer your question.
But let's say that if you really want people to explore your sandbox, what you should do is make like a bouncy ball pit filled with your 3D visualizations.
If somebody wants to come up with the money to fund a playground, I'm all in.
Maybe McDonald's.
A large interactive.
You can actually
Maybe
have
McDonald's will want that.
you can have different objects in the Happy Meals, and then they can have a
That
playground.
might be getting too commercial for my life, but yes, it is public domain, so I guess so.
All right. Any other
so my-
questions?
I just had a quick question. Well, it's kind of just an off question, but I was just wondering when are you going to get together with Fiorella Terenzi and put together an album?
So actually, there are some musical things in the works. I will say there is a record label that has concatenated all of our sonifications into like a full playlist. It's going to be out on like a physical CD and a vinyl, which, by the way, I have a record player, so I'm kind of excited for that. There's a recording artist that's interested in sampling a piece for a piece of music, and we also have a composer who does primarily operatic compositions, working on translating it into sheet music, so that people could play bits of the universe. And I love stuff like that because, I don't know, this whole enterprise of science really does not need to be relegated to just people who are already in it, right? I think these alternative ways of exploring, it's not only about accessibility, but it's really also about just showing that you're open to exploring, that you're open to trying different things, that you're open to how other people, witness the world or experience the world. I don't know, that might sound a little cheesy, but I think it's this idea that when you kind of try something new, try something creative, put yourself out there, people can really respond to the idea of what it is you're trying to do. And so, yeah, I am really excited to see some interest in the music world, because it's just an area that I don't have any connections in. And so having people that are interested in spreading this type of sciencey goodness throughout the world via the enterprise of music is pretty cool. Hopefully.
Great. All right. Well, if there are no other questions, let's thank our speaker again.
All right. Thank you all so much for joining us. We will see you next time.
Thanks.